Hello everyone, I am Krupa John Reddy studying 8th SEM ECE of Sri Venkateswara College of Engineering. Today my topic is FPGA based digital implementation of adaptive synchronization methodology for 60 chaotic system. Going in detail, let us know about chaotic systems, adaptive synchronization methodology and FPGA implementation. So basically, chaotic system describes the qualities of the point at which stability moves to instability or order moves to inorder. For example, like putting a dozen dogs and a dozen cats in the same room would probably lead a utter chaos. So chaos is a state of utter confusion or disorder. The chaotic systems are distinguished by sensitive dependence on initial conditions and by having evolution through pace appears to be quite random. Chaos means like it refers to randomness, like cards or dice, which is unpredictable because we just don't have the right information. Chaos is somewhere between random and predictable. Generally, a dynamical system is called as chaotic system whenever its evolution sensitively depends on the initial conditions. The first chaotic system is proposed by Lorentz for weather model. This topic has attracted the interest of many researchers and is still an important problem in the modern theory of chaotic synchronization. And the chaos synchronization is the important phenomena for digital communication or digital modulation and many more, and many digital information systems. Since the digitalization of chaotic systems and its synchronization methodology is very important in digital information systems, and the researchers found on the FPGA based digital implementation of chaotic systems, as FPGA has high accuracy, short design circuit, low power consumption, low cost. And we all know that FPGA is a reconfigurability integrated circuit, as it designed to be reconfigurable using HDL such as VHDL or Verilog HDL. As we know that FPGA is an application specific integrated circuit. Basically, the FPGA based digital implementation of adaptive synchronization methodology for 60 chaotic system involves designing and implementing an hardware based solution using FPGA technology to achieve synchronization of chaotic systems in 6 dimensions. And there are few steps in this process are involved, which we will discuss in later. And these are my today contents: introduction, detailed survey, methodology, results, conclusion and references. Coming to the introduction, as I told before about chaotic systems and FPGA implementation, here adaptive synchronization is a technique used to synchronize the state variables of two chaotic systems, even if their initial conditions are different. The six-dimensional chaotic system is one of the most studied chaotic systems, and its synchronization has many applications in various fields, such as secure communication, cryptography, and chaos-based computing. With the digitalization and reconfigurability of the FPGA, chaotic systems and their applications can be more flexible. And we all know that FPGA is an programmable logic device that can be reconfigured by the user to perform a specific task. As you know that it is an application specific integrated circuit. It provides high speed processing and parallelism, which makes it suitable for real-time applications. Therefore, an FPGA-based digital system can be used to implement the adaptive synchronization methodology for the 6D chaotic system. And the digital implementation of the adaptive synchronization methodology for the 6D chaotic system involves designing the hardware architecture of the FPGA-based system, developing the software code for the system, programming the FPGA chip with the program with the software code, configuring the system, verifying the functionality of the system by simulating the 6D chaotic system, and testing the system with the real-time data. Here is an overview of the steps that are involved in the process: system modeling and the chaos generation, adaptive synchronization methodology, and the FPGA board implementation, and testing and verification, optimization and refinement, and the deployment. Here, the adaptive synchronization algorithm adjusts the control parameters of the slave system to match the state variables of the master system. After programming the FPGA chip with the software code and configuring the system, the functionality of this system is verified by simulating the 6D chaotic system and checking the synchronization between the master and the slave system. And coming to the objectives, to synchronize the state variables of the slave system with those of the master system using an adaptive synchronization algorithm, and to develop a high speed and low power FPGA based digital system to provide a secure communication and data encryption technique, to offer flexibility allowing for easy modification and adaptation to different applications, and to provide high reliability and low power consumption, making it deal for portable devices. To demonstrate feasibility and effectiveness. These are the objectives that are involved. And next is literature survey. Coming to the first one, robust chaotic shift gain scheme based on electro-optical hybrid feedback system. And the pros, coming to the pros, electro-optical hybrid feedback systems can potentially operate at high bandwidths, allowing for high-speed communication and data transmission. And the cons, electro-optical hybrid feedback systems can be complex to implement, requiring precise control of parameters synchronization. And the next one, new video encryption schemes based on chaotic map. Chaotic maps are known for their sensitivity to initial conditions and parameter values, which can make them suitable for encryption purposes. Chaotic maps are sensitive to initial conditions and parameter values, which can also make them vulnerable to attack if the encryption keys or parameters are compromised. Coming to the third paper that I have referred is synchronization of time delay chaotic systems with uncertainties and external disturbances. And the pros are the paper may propose synchronization techniques that are robust against uncertainties and external disturbances. Coming to the cons, the paper may need to provide sufficient validation and reproducibility of the research, such as by providing detailed experimental setup. These are the literature survey that are papers that have been referred, which is helpful to my topic. Coming to the methodology, initially we are modeling the system. The first step is to mathematically model the 60 chaotic system that needs to be synchronized. This typically involves deriving the differential equations that describe the dynamics of the system. And the chaotic system may consist of multiple variables, and the equations governing their behavior may be nonlinear and exhibit chaotic behavior, like choosing a suitable system with 6 dimensions as the drive system and response system. And the next step is nothing but chaos generation. Like the chaotic system needs to be implemented on an FPGA. This involves designing a digital circuit that can generate chaotic signals based on the mathematical model of the system. This can be achieved using techniques such as discrete time numerical integration or digital chaos generators, which use logic gates and digital arithmetic operations to produce chaotic systems. And the next step is designing an adaptive synchronization methodology algorithm to synchronize the response system with the drive system. And the adaptive synchronization methodology involves designing algorithms that can estimate the parameters of the chaotic system and use them to synchronize the states of two or more chaotic systems. These algorithms typically involve feedback loops and adaptive parameter estimation techniques to adjust the synchronization process in real time based on the measurement states of the system. And further, we need to implement this adaptive synchronization methodology algorithm on an FPGA platform using an hardware description language such as Verilog or VHDL. After the FPGA implementation is completed, now it's testing and verification of the FPGA chip. The system needs to be tested and verified for correctness. Here FPGA plays an important role. So FPGA is basically an reprogrammable so that errors can be reconfigurable easily. Now the system needs to be tested and verified for correctness and performance. This may involve simulating the behavior of the system using software tools or emulators and comparing the results with the expected behavior based on the mathematical model of the chaotic system. It may also involve testing the system on a physical FPGA board and measuring its performance in real time. And then optimization and refinement. Based on the given testing and verification results, the design may need to be optimized and refined to improve its performance or address any issues that may arise during testing. This may involve adjusting the parameters of the synchronization algorithm, optimizing the digital circuit for better performance, or refining the hardware implementation to reduce resource utilization or improve reliability. And at last, once the FPGA based digital implementation of the adaptive synchronization methodology for the 6D chaotic system is tested, verified, and optimized, it can be deployed in practical applications like where synchronization of chaotic systems is required. This may include applications in areas such as secure communications, chaos based cryptography, and chaos control in engineering systems. And here comes the block diagram in which initially the chaotic systems which is given to the analog to digital converter and then adaptive synchronization algorithm and then control signal generator and again back to digital to analog converter and coming to chaos. This is the basic generalized block diagram for the FPGA based digital implementation. Here the chaotic system, which is the target system to be synchronized, is represented by mathematical equations. The system could be a Lorentz system, Rosler system, or any other 6D chaotic system. And then analog to digital converter. The continuous time chaotic system output is converted into a digital system using an analog to digital converter. The ADC samples and quantizes the analog chaotic system output into discrete digital values, which is suitable for the digital processing. And the adaptive synchronization algorithm, which includes chaos synchronization techniques such as parameter estimation, feedback control, and adaptive coupling, which is digitally implemented by FPGA. And then the control signal generator generates the control signals based on the adaptive synchronization algorithm. These control systems are used to drive the chaotic system towards the synchronization with the reference system. And then again back to analog converter, digital to analog converter. The digital control signals generated by the control signal generator are converted back into analog signals using a DAC. These analog signals are then used as input to the chaotic system to drive its synchronization. And the chaotic system interface. The digital control signals from the DAC are interfaced with the chaotic system, providing the necessary feedback control signals to the system to achieve the synchronization. And here the synchronization monitor, which continuously measures the synchronization error between target chaotic system and the reference chaotic system. This error is used as a feedback signal for the adaptive synchronization algorithm to continuously update the control signals and improve the synchronization performance. And the main FPGA is a programmable logic device, as we all know that implements the adaptive synchronization algorithm, control signal generator, synchronization monitor, and digital logic circuits. And here the FPGA is programmed to perform the digital processing tasks required for chaos synchronization and interfaces with ADC and DAC and the chaotic system interface to enable the synchronization of the target chaotic system with the reference system. And the reference chaotic system is the duplicate of the target chaotic system, and its output is used as a reference for the adaptive synchronization methodology to achieve synchronization. Overall, the FPGA-based digital implementation of adaptive synchronization methodology for a 6D chaotic system involves converting the chaotic system output into digital signals, processing them using digital logic circuits in the FPGA, generating control signals and interfacing with the chaotic system to achieve synchronization with a reference chaotic system. The flow diagram for implementing adaptive synchronization methodology for 6D chaotic system, which has basically 6 steps: defining the system requirements and specifications, choosing a proper FPGA, designing architecture and modules, implementing hardware and software components, testing and verifying, and then deploying. Coming to the results, FPGA-based digital implementation of adaptive synchronization methodology for a 6D chaotic system presents simulation results demonstrating the effectiveness of the proposed methodology for achieving adaptive synchronization between the drive and response systems in a 6D chaotic system using FPGAs. And the simulation can be done using MATLAB and Simulink and compare the results with those obtained using an conventional fixed parameter synchronization method. And the proposed methodology can be implemented using VHDL programming language and Xilinx ISC software on FPGA board, or we can use Vivado. And the hardware implementation of the proposed methodology shows that it is unfeasible and can be implemented in real time. Overall, the simulation and the hardware results demonstrate the effectiveness and practicability of the proposed adaptive synchronization methodology for 6D chaotic system using FPGAs, which can have applications in various fields such as secure communication and chaos-based cryptography. Here, the figure 1 represents the synchronized state variables in which the variables which has to be synchronized, and the figure 2a represents the error signals, and figure b 2b represents the adaptive controller signals. So in numerical solutions, the initial conditions for master and slave 60 chaotic systems are taken as respectively, and the initial values for unknown parameters are taken as alpha, beta, gamma, and are respectively taken. And the figure 2a, as you know, that represents error signals that reaches the zero when the systems are synchronized together. And figure 2b represents the adaptive controller signals, which become zero when the master and slave systems are synchronized together. And coming to the applications, these are widely used in secure communication, robotics, cryptography, control system, medical application. The final conclusion, six-dimensional chaotic systems is introduced and adaptive synchronization methodology for a 6D chaotic system is explained. And we have designed a new adaptive controllers to achieve the complete synchronization of six-dimensional chaotic systems. Here the MATLAB results give to prove the efficiency of the proposed synchronization methodology, and the proposed methodology is implemented in FPGA, and the Xilinx simulation results are shown to validate and demonstrate the main results derived in this paper. And also generators provide an efficient way to design a dynamic nonlinear control system using FPGA board with hardware simulation. And the controller performance were such that the complete synchronization of the six-dimensional chaotic system have been achieved. Therefore, reconfigurable devices provide a very powerful tool for the control of complex nonlinear systems. And the given six-dimensional chaotic system consumes the source of FPGA most. And these are the few references that we have taken to describe about my topic to discuss. This is a brief explanation that how we are designing and implementing an hardware-based solution using FPGA technology to achieve synchronization of chaotic system in 6 dimensions. Thank you.